morning, everybody. 400 years ago, Galileo pointed his telescope at the sky. And ever since then, we've built bigger and more powerful telescopes to look at the sky in increasingly more detail. And while we've learned a lot, there are some problems that we still can't answer. Today, I'm going to describe to you the things we still don't understand about the universe and how we in Australia are going to take a new approach to try and answer them. So I'm going to start by putting the entire history of the universe on one slide. So here it is. Pretty amazing that we can do this. The Big Bang at the top, and us 13.7 billion years later at the bottom. So we know the universe began in this huge explosion, a Big Bang. We know that for a long period after that, not much happened. The universe was dark, gas was floating around in that darkness. We call that period the Dark Ages. Then after about 1 billion years or so, these clouds of gas collapsed under gravity and formed stars and galaxies. Let there be light, as someone once said. The stars turned on. You might call this the cosmic renaissance. We now have stars and galaxies, and for billions of years they have evolved, collided, aged, and eventually giving birth to the sun, the solar system, and us, and we now look at the sky and try and understand it. And while we know a lot about the beginning, we actually know quite a lot about the Big Bang, except the minor detail of why it happened in the first place. And we know a lot about the universe now, but there's that big gap in between the Dark Ages and the Cosmic Renaissance. We don't know how we got from the Big Bang to us. So we have a problem. We don't understand how the universe has evolved. There's a second problem. The universe is changing, and it's changing quite quickly. In December of 2004, a little star about 50,000 light years away gave off a sudden flash. For a quarter of a second, the star was brighter than the Milky Way by a factor of 1,000. This intense radiation hurtled across space and crashed into the Earth's atmosphere, lighting up the ionosphere and knocking out satellites all over the world. Now, luckily, we happened to see that when it happened. A quarter of a second it was on and then it was gone. But it turns out there are explosions like this happening all over the sky every day. We don't understand what they are and what they're telling us, and unless we're looking at the right place at the right time, we normally miss them. The universe is dynamic. Not only do we not understand it, but we're not even seeing the whole story. And there's a third problem, a very minor problem, that we don't actually know what the universe is made of. Now, the stuff we think about when we look at the sky, galaxies, stars, planets, trees, people, they're all made of atoms. We think we understand atoms. But atoms are only 5% of the universe. There's a lot of other stuff out there, stuff that we can't see and we don't understand. About 23% of the universe is something we have no idea what it is, so we just call it dark matter. But if that's not bad enough, 72% of the universe is filled with something even less understandable, some sort of mysterious anti-gravity force called dark energy. So 95% of the universe is completely mysterious. Or as my colleague Bob Kirshner likes to say, the universe is like Los Angeles. It's only 5% substance and 95% energy. So the universe evolves and we don't understand that. The universe changes, we don't understand that. And the universe is dark, and we don't understand that either. We haven't really done much in the last 400 years. So why don't we understand these problems? We've got these amazing telescopes. What is the problem? The problem is that the answers to these questions are not buried in individual objects that we can study in great detail. So here is sort of a typical picture from the Hubble Space Telescope, the most powerful telescope ever built. You've seen these breathtaking images of incredibly distant stars. But the answers to these questions are not in individual objects, but they're written on the whole sky. They have subtle imprints that you need to look at the whole sky at once to get the answers for. And so to show you the contrast between the Hubble Space Telescope and the whole sky, here is what Hubble sees, and let's just see how much of the sky we see every time we take a picture with Hubble. So there's a nice galaxy, there are some stars that we're still going, and this is about a quarter of the sky. So you can see that Hubble is only telling you a tiny, tiny part of the story. You need to take this new approach of all-sky astronomy if you really want to see what's going on. So why don't we do that? Why don't we just point Hubble all over the whole sky? Well, there are three problems. There are three reasons why we can't do this all-sky astronomy just yet. The first is that our telescopes simply can't see that much of the sky at once. So as I said, the Hubble Space Telescope, best telescope ever built, billions of dollars, let's ask it to take a picture of the moon. Surely that's a bit embarrassing. You're not going to ask something as amazing as Hubble to take a picture of the moon. Surely that's way beneath its capabilities. Well, it turns out Hubble can't take a picture of the moon because it has too small field of view. In fact, they tried to make a picture of the moon. It took them many, many days, and this is how much of the moon they were able to cover. Because Hubble has a tiny field of view, and yeah, well, we know Hubble's great, so that's what Hubble saw, beautiful picture of a tiny part of the moon. But you can see that if you want to image the whole moon, let alone the whole sky, you would need to build an entirely different type of camera to the ones we're used to building. So that's problem number one. So okay, let's suppose that you built some amazing camera that can do a lot better than Hubble and that can see the whole moon. So if you've done that, you've got a new problem, and that's that you are going to be generating a lot of data. So data isn't such a big deal anymore. We're pretty blasé about data. I'm sure many of you have iPods, and a 160 gig iPod, the biggest one you can get right now, well, 160 gigs is an insane amount of data, thousands and thousands and thousands of songs. Not many people have a music collection big enough to fill up an iPod. But let's consider if you built one of these cameras that can look at the whole sky, how much data you would generate. Well, let's consider how much data you would generate in the first second. Okay, well, you'd certainly fill up one iPod in the first second. You would easily fill up 10 iPods. Well, it turns out that in the first second, you would fill up 500 160 gigabyte iPods. And that's after 1 second. Imagine how much data you would accrue if you looked at this telescope, used this telescope to look at the sky all night, or maybe all year. So even if you could build a telescope that looked at the whole sky, we simply don't have hard drives that are big enough or fast enough to store the data. We have to have a new way of dealing with this incredible torrent of information that would be coming in from the whole sky relentlessly before we even had time to even think about what to do with it. So let's suppose you've solved this problem too. You've got your amazing telescope and you've somehow dealt with the endless iPod problem and you're somehow saving all the data somewhere. So now you have this incredible data set. So how does a scientist look at this data and make sense of it? This is the ultimate needle in the haystack problem. Somewhere in your data set is the answer you're seeking. And unless you know where to look, you're simply not going to find it. So here's a sort of a simulated data set that we might get from one of these new telescopes, and there's some subtle answer buried in it. But unless you know where to look, you're not even going to know where to start. So three questions about astronomy and three big problems that we need to solve if we want to build the telescopes. But what's really exciting is that here in Australia, we are about to turn on telescopes that can solve all of these problems and that can answer all of these questions. So for example, I talked about this problem of needing new cameras that can look at the whole sky. Well, we're doing that. In Coonabarabran, about 7 hours drive from here, we have a telescope that has a 268 megapixel camera. So your camera might be quite fancy. It might be 10 megabytes or 10 megapixels, 15 megapixels, or 20 megapixels. This is 268 megapixels every time you hit the shutter. So with this sort of amazing, powerful, unprecedented technology, we can take pictures of the sky that are wider and more detailed than anybody has done before. So this is just a more traditional optical telescope where you peer through the eyepiece, at least so to speak, and take normal photographs of the sky. But we also here in Australia are very good at radio astronomy. So here is some radio telescopes that we're building in the desert in Western Australia. And you might think that these look like normal radio telescopes, but look carefully. At the focus isn't a tube or a small camera, but a big, heavy box. And that box is a whole new type of technology, sort of this electronic checkerboard that essentially gives this dish fisheye lens technology. That instead of pointing the dish at one particular place, the dish can now see a huge patch of the sky. And so just to show you what a big patch of the sky we're talking about, here is the moon again. And there is that tiny piece of the moon that Hubble can see. So how much of the moon can you see with these telescopes? Well, you can see a lot more than the moon. So there's the moon. And here, well, okay, the astronomers amongst you will know the moon never actually passes near the Southern Cross. So forgive me for that gross error. But you can still see the moon there. That's how big the moon would look on the sky if it moved past the Southern Cross. And that's how much of the sky that you can see in one go with this new type of technology. So you can't just image the whole moon. You can image hundreds and hundreds and hundreds of times bigger than the full moon. And so this is after one snapshot. Move the telescope a bit to the side and take another one. And you can very quickly see that you can fill up the whole sky, and we can realize our dream of all-sky astronomy, of seeing the whole sky pretty much in less than a day. We can do what used to take a year or 10 years or 50 years, we can do in one night, look at the whole sky. And when we're done, we can do it again the next night, and we can see what's changed. So this is a whole new way of doing things, and as I said, it's happening right here in Australia. So this is very exciting. Astronomers are going to learn a lot from this, but you, the public, might say, well, what am I getting from my tax dollars? Because it's you that's paying for it. Thank you for doing that. So the important thing to realize is that we are asking questions that have never been asked before. And we are asking our engineers to build instruments for which the technology simply doesn't yet exist. And when you do this, you inevitably find approaches and discoveries that change the world. So let me give you one example. This is an astronomer, John O'Sullivan, an Australian astronomer from Sydney. And in the 1970s, John was trying to study explosions from evaporating black holes, as you do. And he realized that current technology at the time in the 70s was not capable of detecting flares from exploding black holes. So he developed a new electronic chip, a new algorithm to do this. Didn't see anything, unfortunately, which is why we're still looking for these things. And a few years later, he realized that this might sort of be interesting and useful for other things, and he wrote a patent for it. And they eventually realized that the same algorithm that you use to develop exploding black holes is the same algorithm that you can use for computers to use the internet without wires. And that eventually became Wi-Fi. You all use it every day, thanks to an astronomer who was looking for exploding black holes. So we're quite proud to say here in Australia, it was an Australian astronomer who invented Wi-Fi. So I don't know what we're going to discover or invent with our telescopes, but we are trying to push the envelope and do things that have never been done before. And you can be guaranteed that likewise, we are going to develop technology that's going to have all sorts of unexpected applications. But that's, of course, not why I do it. Astronomers get out of bed in the morning because we want to discover things. Actually, we don't get out of bed in the morning, we get out of bed at night, but it's another story. We want to discover things. I am part of this. I'm participating in this journey because we want to build new technology. We want to see things like the first stars turning on. But every astronomer knows that the things you think you're going to discover with a telescope are never the things that you actually do discover. This idea of serendipity has been around in astronomy for a long time. There was an astronomer back in the 16th century, I think he was Danish, his name was Hamlet, and he said to his PhD student Horatio that there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. He was telling his student Horatio that there's just so much out there that we can't even be aware of. There was a 21st century astronomer that really captured things, though, that one whom we all very much admire. And he said there's sort of three types of things in astronomy. There are things that you really know have to be out there, distant stars and galaxies. He said there are known knowns, there are things that we know. I think you all know who this astronomer is. He said there's also some known unknowns. There are things like the first stars turning on that we do not know. They're out there, but we don't really understand what they are. But the really exciting thing about astronomy, the reason why we spend all night looking through our telescopes hoping to discover things, are of course the unknown unknowns. The things that we don't know that we don't know. The things that will change the world that we haven't discovered yet. The things that I hope, if the organisers let me, I can come back and tell you about in TED, say, 2021. So the message I want to leave you with is that there are some big problems out there that we are about to embark on a very exciting journey to discover them. And the most exciting thing is that that is all happening here in Australia thanks to clever Australians. Thanks very much.